right, so here's a solid object, and here's a model of the solid object. The atoms are in fixed locations, and the forces between these atoms are modeled by these springs. Okay, here's what we're going to do. We're going to heat this solid. So we're going to heat the solid. What is going to happen when you heat it? So the atoms will vibrate with greater amplitudes. You're adding potential energy, and so the solid will expand. The distance between the atoms will increase. Okay? The distance between every atom will increase. Okay? And as a result, the solid will expand. Okay, and this is of interest to us for many of our applications. Okay? So that's why we're learning this. Okay? Now, will the width increase as well?
Yes.
Every dimension will increase. Okay? But if the length is the predominant dimension, the change in length will be the greatest, and so that's what we'll concentrate on. Okay? The width will also increase by the same factor and all that. Okay. So the increase in length is equal to the original length times the increase in temperature times a number that depends on the material. And this is called the coefficient of linear expansion. Okay? So that's the coefficient of linear expansion. All right. So here, and this number is important enough where they give you a table. Okay. So for various materials, here's the coefficient of linear expansion. Okay.
Same value, why is it different for volume expansion?
Okay, so for the same material, it turns out that the volume expansion is 3 times the linear expansion. Okay. All right, let me illustrate this number. So let's say we take an aluminum rod, and it's 1 meter long. We'll heat it by 1 degree Celsius. Okay? So 1 meter aluminum rod, and the increase in length will be 1 meter times 1 degree Celsius times 25 into 10 minus 6 per degree Celsius. Okay. So the increase in length will be 25 into 10 to the minus 6 meters, 0.025 into 10 minus 3 meters, which is 0.025 millimeter. Okay, there's a millimeter. You take aluminum rod, 1 meter aluminum rod heated by 1 degree Celsius. Its length increases by 2/100th of a millimeter. The increase is 25 parts in a million. Why do you care about it?
So you're saying like a frame, and it's increased by a lot, and it's a very big piece, it's going to increase a lot, especially all metrically, but with a long space.
So look at this. This is an expansion gap. Okay, you have to do this in bridges and stuff like that. If you don't leave an expansion gap when it gets hotter in the summer, okay, if this expansion gap was not big enough, here's what would happen. So the train tracks also have expansion gaps. And you see the expanding material, the forces would be so large that it would deform the material. On the sidewalks, you see those lines, the cuts, those are thermal expansion gaps. Okay, so you have to build all this in all places. Okay. This bridge in Michigan has a length of 1,100 meters. 1,100 meters is from here to the speedway. Okay. It sees a change in temperature of over 100 degrees Celsius between the dead of winter and the peak of summer. And so if it was one single span, its length would increase by 1.5 meters, which is your height. Okay. So those expansion gaps have to add up to 1.5 meters. Yeah. So if you didn't have any expansion gap, it was one solid piece, you would have to, at the end, you would have to accommodate for that. Yeah. So here's the gaps in the winter, and there it is in the summer. So here's a little application. Okay, now that you know this. Okay, see, you can take two materials. See, this here's iron and steel and aluminum. You can see that aluminum expands twice as much as iron. So here's something you could do with it. One can be aluminum and one can be iron. You heat it. Oh, so the bottom one would be aluminum, and the top one would be steel. You heat it, the aluminum expands more, and this thing bends in that direction. Okay, so this could have an electrical contact, and it could be a heater. Once the room gets warm enough, you would lose electrical contact, and it'll shut down the heat. Okay, so you could build a thermostat that way. So this is called a bimetallic strip. You can use this in control applications. By the way, the Trans-Siberian line, which goes across Russia, is almost 10,000 kilometers across, and the gaps in the train track have to amount to 8 kilometers. All the gaps have to add up to 8 kilometers. 8 kilometers from here to Ormond Beach. Here's another interesting fact. Okay, so let's say here's a aluminum washer. Okay, let's say you have a aluminum washer like this, and you heat it. You know how aluminum would expand. Now the question is, how does this gap expand? I'm sorry?
It's also going to expand with the material.
So it'll expand as if this gap in the air will expand as if whatever material this thing is made of. And that's what this thing is illustrating. Yeah, so you're right. So imagine a complete disk. You heat this disk would expand like that, and you see that inside disk would expand, the gap would expand exactly like that. So for instance, this kind of stuff is useful for the following. Okay, planes are made of aluminum shells because you got to make them light. Yeah. Now try and screwing an aluminum panel. Aluminum is soft, and you would strip all the screws. So how do you get around that problem? So here's how you get around that problem. So you make the socket size, and you make the screw just slightly larger. But the problem is going to get worse. You try to screw that, and you're going to strip it. So what do? Take the screw, dip it in liquid nitrogen, and then put it in. All right. Here we're doing the opposite. See this ball wouldn't fit in that socket. You heat that, that expands, you fit the ball in the socket, and then let it cool down. Yep. All right, so this formula tells you area expands 2 times alpha times area times delta T. Volume expansion is beta times volume times delta T, and beta is 3 alpha. Okay. Here's an interesting graph. This is for fresh water. Okay. And what this plot is plotting is density versus temperature. Okay, let's see what's interesting about this. The density of a material is defined as mass divided by volume. Okay, so if you heat a material, what happens to the volume?
It increases.
The volume of most substances increases. And what would happen to the density? You heat a substance, you're not changing its mass. If you increase its volume, the density should decrease. For most substances, and it happens for almost all substances. Look at this for water. You're increasing the temperature in this small window from 0 to 4 degrees Celsius. You're increasing the temperature, and the density is increasing instead of decreasing. It's a very small effect. See, this is 10 parts in 100,000. Very small effect, but this is extremely important. So here's an interesting story associated with that. So let's talk about that. So you saw that in the small window, 0 to 4 degrees Celsius, as the temperature increases, the density was also increasing instead of decreasing. All right. So here's why that is important. Here's a lake. Let's say I want to freeze the lake. Do you know how to freeze a lake? What's that? Yeah, exactly. So flip a switch, make the air cold. Heat will start flowing. So let's say initially the lake was at 10 degrees Celsius. This is warmer than that. Heat will start flowing from here. Okay, let's say this top layer cools down to 4 degrees Celsius. What has happened at 4 degrees Celsius?
The density begins to decrease.
At 4 degrees Celsius, its density is the highest, and that water will sink. So that'll be 4 degrees Celsius. Okay? Then eventually, so this layer will be at 4 degrees Celsius. And eventually the whole lake will get to 4 degrees Celsius. Then this will get to 2 degrees Celsius. But this is less dense than that, and that won't sink. Okay. So all this is 4 degrees Celsius. This top layer is 2 degrees Celsius. It'll cool down further. It'll become 0 degrees Celsius. It'll freeze. And ice is less dense than water, so it won't sink. Now, ice happens to be a good insulator. Okay? Now it'll stop heat flow. Okay? So you can have this temperature all winter long. You can try your best all winter long, and this lake is not freezing. All you have is a top layer of ice. And this is good. Fish can survive there. Okay, so this is important for life. You can't freeze a whole lake. All thanks to this little bump in the ground. You guys know what heat means now. Okay, so at any given temperature, these guys have random kinetic energy and random potential energy. That's the internal energy. And when you bring this in contact with an object at lower temperature, this internal random energy is what is exchanged, and that is the heat. Okay? Heat is the internal energy transferred between objects because of temperature difference between them. Okay? So we now know this, but 300 years ago we didn't know this because we thought heat was some kind of a fluid. Okay? So once we figured out that heat was a form of energy, it was random mechanical energy. It became important. So before we knew that, we had a unit for heat, which was calories. You guys know how calories are defined? What is 1 calorie? Okay, so here's the definition. 1 calorie is the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Luke, hold up your bottle. So 1 gram of water is about that cap full of water. So to heat that cap full of water by 1 degree Celsius, you need 1 calorie of heat. A food calorie, by the way, is 1,000 calories. So 1 food calorie is a capital C is 1,000 little calories. Okay. So anyway, heat was defined in calories, and then mechanical energy was defined in joules. So, but once we realized heat was a form of energy, this conversion became important to figure out. Okay? And here's how Mr. Joule did this experiment, and that's why we named the energy unit after him, Joule. Okay, here's what he did. So here's paddles. When this guy falls down, what he does is he spins the paddle, which warms the water. Okay, so when this falls down, he loses this much energy. And when the temperature of this guy rises, so the mass of water times the specific heat of water times the rise in temperature. This was calculated in calories, this was in joules. And then you know the conversion. Okay? So that's how we got this factor. Okay, do you guys know how breezes happen?
Different temperatures of air having different densities pull each other.
Okay, how do you get air to flow? How do you get any fluid to flow? For any fluid to flow, you have to have high pressure and low pressure, and fluid will flow from a high pressure to low pressure. Okay, so that's how you make. All right, now how do you get the air to move? Okay, so here's what we'll do. Okay, so this is a grassy area. This is asphalt. So Walmart parking lot. Well, equal amounts of sunshine are falling on both these patches. This guy gets hotter because he absorbs the heat better. Okay, and so this air gets warmer than this air. Okay. So this air gets warmer than that air, than that parcel of air. This gets lighter. When you warm air, it expands and it gets lighter than the surrounding air, and it will rise up. And as this air rises up, it leaves behind a partial vacuum, it leaves a low pressure area. This colder air head was at a higher pressure. And now you'll have a breeze. At night, this guy will lose heat faster. Okay? This guy gets colder and the pressure is higher and the breeze will reverse. Okay? That's emphasized here. Yeah. Okay, so this is introducing the concept of specific heat. What this is saying is, so let's say you have so much of some stuff. Okay, I want to warm it. I add this much heat. Q is used for heat. That's the amount of heat added. Well, how much did this temperature rise? If you add Q amount of heat, M is the mass of the substance, and we're talking about solids and liquids here. C is the specific heat, and delta T is the rise in temperature. Okay, now let's say you add the same amount of heat, and if the specific heat of the material is high, the temperature rise will be lower. Right? Everybody understand that? So you add a certain amount of heat, let's say 100 joules of heat, to 1 kg of material. If the specific heat is high, the rise in temperature will be low. If this is high, okay. So here's a table of specific heats. See, there's a specific heat for water, 4,200 joules per kg per Kelvin. What this means is you need 4,200 joules of heat to raise the temperature of 1 kg of water by 1 degree Kelvin. That's what that number means. Okay, here is silicon dioxide, essentially. A lot of dirt is that. So for dirt, there's the specific heat, 700 joules per kg per Kelvin. The specific heat for water is 6 times greater. Yep. So let's say during the day, you have equal amount of sunlight falling on land and water. This thing gets, in principle, 6 times hotter. The temperature rises that much higher. Okay. You leave a low pressure here, you have a high pressure here, breeze blows like that. At night, the land gets cooler faster. The water holds it takes a lot of, you need to remove a lot of heat to cool down water. So this is warmer. And this air rises, and you have a higher pressure here, and you have a breeze flowing like that. So during the day, you get a breeze from the ocean, or the body of water, and at night, you're getting a breeze from the land. So if you have property here, you always have a nice cool breeze. And you have a pretty view as well. So that's why that property is expensive. Yeah. Okay. What is latent heat?
During a phase change, when you melt ice, it takes a specific amount of heat to melt, different than changing the temperature.
I'm sorry?
Different than changing the temperature.
Okay, so it's called latent heat because, you're right, okay. So let's say this is water, you heat it, you add heat, and when you don't have phase change, the temperature will rise. Okay. let's say you take a bunch of ice, which is at 0 degrees Celsius, and heat it, what will happen?
It's gonna melt.
Yeah. So let's start off with the following. Let's take it at minus 5 degrees Celsius. You heat it. What will happen is the temperature of ice will rise up to 0 degrees Celsius. Okay? Till then, nothing will melt. Only when it gets to 0 degrees Celsius, now the ice starts melting. And once it starts melting, the temperature is not rising. You're adding heat, and the temperature is not rising. When you were adding heat here, the temperature was rising, and it wasn't melting. Okay, so where is all this heat going? You're adding heat.
It's breaking the bond in the water.
It's breaking the bonds. And that is latent heat. Okay. So the latent heat is the heat that you've added that didn't raise the temperature. Okay. And so in this case, it was breaking the bonds and it was raising the potential energy of the system. Okay. So latent heat is the heat added. Okay, so this is the heat added to a system. Now we're talking about solids and liquid when the temperature is changing. And this is the heat added during phase change, L for latent heat. Okay. So during phase changes, heat added does not raise the temperature of a substance. The energy required to and that is the energy needed to overcome the intermolecular phase forces. So you're breaking these bonds. Okay, so the heat added is the mass of the substance that has changed phase times the latent heat. Okay? When a substance goes from solid to liquid, that's called latent heat of fusion. When it goes from liquid to vapor, it's called latent heat of vaporization. Okay? All right, so that's what this graph is showing you. So here's ice at minus 20 degrees Celsius. You are adding heat, and the temperature of ice rises. When it gets to 0 degrees Celsius, then ice starts melting. And once all the ice melts, you've added heat. When all the ice melts, that's when you can raise the temperature of water. Okay. So if you have an ice-water mixture and you add heat, it'll remain at 0 degrees Celsius. All the heat, see, this nature won't allow the water to rise in temperature. And you could think of part of the thing rising in temperature. So all the heat will go into melting the ice. Okay. Once all the ice melts, then the water temperature can rise. Okay, same thing happens. You are heating water. Once it gets to 100 degrees Celsius, then the temperature doesn't rise till all the water becomes steam. And then once all the water has become steam, then you can raise the temperature of steam all you want. Okay. Latent heat of fusion for water is that, and latent heat of vaporization for water is that. That's joules per kilogram. Okay. Now, it's easier. These big numbers are hard to remember, but this small numbers are easier to remember. So here's a number that you can easily remember. So latent heat of fusion for water is 540 calories per gram. What does that mean?
It's going to release that much energy by cools down.
So to convert that much 1 gram of water to steam, you need 540 calories of heat. Okay. To melt 1 gram of ice, you need 80 calories of heat. So now you might understand the following. Okay. Okay, so I'm sure you've all heard this. What would you have rather done? I'll throw 1 gram of 100 degrees Celsius water at you, or 1 gram of 100 degrees Celsius steam at you?
Water,
No water. Why?
because the steam is 540 calories per gram hotter.
It has that much more energy. So you throw this thing, it condenses to water and burns you with 540 calories, and then it's still water at 100 degrees Celsius. It'll burn as much as that. Okay? So firemen know not to mess with steam, because steam burns are bad. All right. Okay, so what is this? This is a thermodynamic system. Okay? This is a pretty amazing thermodynamic system. Okay. The basal metabolic rate of a thermodynamic system is 80 joules per second. Okay, so so you're using energy at 80 joules per second just sitting there, and you're not doing any work. So eventually all that energy gets converted to heat. So you're all a 100-watt bulb right now. But if you didn't get rid of that heat, your temperature would rise, and then you don't like that. What is your body temperature? Normal body temperature?
98.6.
Yep. So 100 degrees Celsius, 100 degree Fahrenheit, you get to 101 degree Fahrenheit, and we're all crying. Your temperature changes by 1%, and we all cry. Okay? So we maintain a constant body temperature. So you're producing 100 joules of heat per second. So if you don't want your body temperature to rise, you got to get rid of that 100 joules of heat per second. You go for a run, now it's 1500, you're producing 1500 joules per second. Your air conditioning suddenly has to work 15 times harder. Just like that. Can this air conditioner work 15 times harder just like that? No. So how do we do it?
So we sweat.
Yeah, okay, so sweat, big deal. So you're right, we do sweat. Now, what you hope like hell that the sweat evaporates. And every time 1 gram of sweat evaporates, it takes away 540 calories of heat. And that's how we cool down. So for instance, if you put a treadmill in a sauna and run on there, you can sweat all you want, your sweat won't evaporate. Yeah, and that would be bad news. So we take advantage of these numbers. Yeah. So when sweat evaporates, it removes heat from our bodies. Yeah. So here's an interesting fact. Our cooling system is extremely efficient. It's claimed that people have survived temperatures of 260 Fahrenheit long enough to cook a steak. So anyway, the claim is the following. Here's a person and here's a steak, 260 degree Fahrenheit. You put them both in at the same time. This thing cooks, and this person walks out. So that's the claim. We don't know if he was hungry enough to eat that afterwards, but that's the claim. All right, now this just illustrates how much energy nature moves. Okay. So here's a lake. So Lake Superior is about half the size of Florida. So roughly there. Yeah. During the winter, as much as 150 centimeter thick layer of ice is formed on the lake. So roughly my height. All right. Here I have 1 gram of water. What do I need to do to convert it into ice? I'm sorry? How much heat? 80 calories. Okay. I need to remove 80 calories of heat to turn it into ice. Now imagine I need to make this much ice. I'd need to remove a lot of heat. Okay. Well, how much heat would I need to? And by the way, how do you remove the heat? You already learned how to remove the heat. How do you freeze a lake? Make it cold. Make this temperature minus 30 degrees Celsius or whatever. So, to make that much ice, you would need to remove heat as much as contained in 10 million atom bombs. The kind that were dropped in Hiroshima. You have to remove that much heat. And then what do you do 4 months later?
Put it back.
You put it back. You melt all that up. Okay. So that cold air coming, these guys are happy about that, as the lake freezes. All that heat from the lake warms that air, and these guys are happy about that warmer air. All right. Okay, for today, what we're going to do is, there's still quite a bit of lecture left. I'm going to ask you to study the problem solution online. Okay. What we're going to do is, next Tuesday will be your first test. Okay. And then we'll have Wednesday, Thursday, and then next Monday you won't have a test, but we'll have a test the following Monday. Exam 2 will be. Okay? So we'll get ahead, but that's going to be the schedule. All right, so let's see what this diagram is showing you. So here's a fire. You hold a metal rod and stick the metal rod in the fire. What will happen is heat will be conducted across this metal rod and you'll feel the warmth. Why are you feeling the warmth here? How is the heat being transferred to you? Part of it is being radiated. Okay, what is happening is this fire is warming the air around it. This air is getting it's getting less dense than this air, and this air is rising up. So convection is giving you most of the transfer of heat. There is radiative transfer as well. You can feel heat here. Convective transfer is in that direction. This is radiative transfer. So here's an interesting diagram. Okay, so this got lighter than surrounding air, and it had a buoyant force, and that is possible only in a gravitational field. So here's a candle. So this is a candle burning on Earth. This air is getting warmer, which is rising and making this flame in that shape. Here's a candle burning inside the space shuttle. And the gravitational field is, you don't have a flame like that, in zero gravity. Yep.
Does that mean like on other planets with much higher or much lower gravity, the flame would be different shapes?
Yep, so on a stronger gravitational field, it would be narrow. So on Jupiter, if you happen to go to Jupiter and light a candle, the field will be narrow. On the moon, it'll be more rounded. All right, so heat transfer can happen via these three mechanisms: conduction, convection, and radiative heat transfer. Okay, and now we'll look at that. So here is a solid. Okay, when this end of the solid is hotter, these guys have more energy than these guys. And here's how conductive heat transfer happens. This guy, he's not going anywhere, he's just vibrating in his location and transfers some of his energy to him. This guy transfers some part of the energy there, and so on. Okay, so these guys do not leave their average location, they don't leave their location, but they're just transferring heat to their neighbors. Okay, how long does this go on?
Until it's in equilibrium.
Yep. So when all of them have the same amount of energy, when the temperature is the same throughout the table, conductive heat transfer will stop. Net conductive heat transfer will stop. Okay, they will be in thermal equilibrium. So we are interested in, as engineers, we are interested in the rate of heat flow. Okay, how much energy is flowing per second? Why are we interested in this?
So
Yeah.
we calculate how long something can be in contact.
Yeah, right now it's hot outside. We're keeping this cool. There's heat flowing in through that wall, and it's costing us money to keep this place cool. Okay? So if we can decrease the thermal conductivity of the walls, our cooling bills will be smaller. So we are interested in this heat flow, rate of heat flow. Okay, so how much heat is flowing per second depends on the thermal conductivity of the walls, the area of the walls, the temperature difference divided by the thickness of the wall. This is the temperature gradient. Okay, so to maintain this temperature right now here costs us less than in the Sahara Desert. Okay? So, higher the temperature difference, higher the rate of heat flow. Okay? So this temperature gradient is written as dt by dx. Okay, and the temperature is decreasing in that direction, in the direction in which heat is flowing. This would be negative dt by dx. So that's why we put in the negative sign there to make that positive. Okay. So power, the rate of heat flow is dependent on thermal conductivity and the area of cross section and so on. Okay. By the way, here's an interesting application. So how much heat are you producing? What are you? Like a 100-watt bulb. You're producing 100 joules per second. This little device is also producing that much. Yeah. Now this guy, okay, so the chip is somewhere there. That chip is producing about 100 watts as well. Yeah, 100 joules per second. So if the chip warms up too much, then it won't function properly. So you have to cool it. Okay, so a desktop consumes 100 to 150 watts, laptops about 100 watts. Again, generally higher the chip frequency, higher the power consumption. So most of your electrical energy is converted to heat. So this metal block conducts the heat away, and then the fan transports, via convection, transports the heat to the surrounding air. Transfers the heat to the surrounding air. Okay, server farms can have up to 10,000 CPUs. So a room like this can have 10,000 CPUs. So 10,000 times 100. That's 10 to the power of 6 watts. A room like this, you're producing 1,000,000 watts of heat. That's roughly 1,000 homes. In a home, you produce 1,000 watts of heat. Your fridge and all that. So your air conditioning better not fail in this room. Okay. So heat removal can be a challenge, and so you have to plan for all of that kind of stuff. So convective heat transfer. Here's a space heater. This warms up the surrounding air, which rises up. That gets replaced by a packet of cold air, and eventually all the air in the room is warm. Okay? This is a rather inefficient way of heating the room. Okay, you are here, and initially most of the hot air is over there. Okay. But anyway, this convection happens when you're heating water as well. Okay, so this convective cell, this water gets heated first. It gets lighter than the surrounding water, rises up, and it gets replaced by colder water. Okay. So anytime you're heating a liquid, you set up convective currents in there. Now we can't give you a formula for convective heat transfer because that's hard. So we gave you a formula there, but not for convective heat transfer. All right, so here's how nature transfers heat by convection. See, this is near the equator. This gets more sunlight than these guys. This water gets warm, and then this warm water gets transported all around the globe. Okay, so the currents transfer heat all over the globe, and that's important for life, nutrients, and all that kind of stuff transported. Okay. So this currents, this is Mr. Ponce de Leon discovered these currents. Here's how he discovered it. This current was flowing at about 5 miles an hour, and he was sailing in this direction. The winds were in his favor, but he was going nowhere. That's how he found this river of warm current, the Gulf Stream. Okay. The Gulf Stream is typically about 100 kilometer wide, which is half the width of Florida, and 800 to 1,200 meters deep. Okay, so this river is 100 kilometers wide, half the width of, and 1 kilometer deep. 1 kilometer is from here to the speedway. Okay. The current velocity is about 5.6 miles an hour, about 5 knots. Okay. So even if you had 5-knot winds helping you, you're not going anywhere. The current velocity is fastest near the surface. Okay. So here's some Gulf Stream patterns. Okay. Gulf Stream transports water at a rate of 30 million cubic meters per second through the Strait of Florida, 30 million cubic meters, and it gets to 150 million cubic meters per second here. And this water is enormous. The volume of Gulf Stream dwarfs all rivers that empty into the Atlantic combined. So in the Atlantic, what are the rivers? Mississippi and the Amazon are the two big ones. And they only dump 0.6 million cubic meters. So that's 300 times greater. Water is greater than that. All right. So we saw heat transfer via conduction, convection, and now we'll talk about heat transfer via radiation. Okay. What objects emit electromagnetic radiation?
Everything with energy,
I'm sorry?
everything.
Everything emits electromagnetic radiation. You are emitting electromagnetic radiation. Okay? But you're mostly emitting in infrared region, and so if it's totally dark, then I couldn't see it. Okay? What this is saying is the power radiated, energy radiated per second by an object in electromagnetic radiation is, this is emissivity. It's a number that, it's something that depends on the surface, okay, surface properties. Okay. Well, depends on the it depends on the property of the material. Sigma is a universal constant. That's the Stefan-Boltzmann's constant. A is the surface area of the object, and that's the temperature in Kelvin. And the power emitted depends on the temperature to the power 4. So you double the temperature of an object, 2 to the power 4 is 16 times 16. The object will radiate 16 times more energy. So if the surface temperature of the sun were raised from 6,000 to 12,000 degree Kelvin, we couldn't live here. We'd be getting 16 times the energy, 16 times the power. Okay? So it's very sensitive to the temperature. Now you're emitting electromagnetic radiation. How about the wall? Is the wall emitting electromagnetic radiation? Yes. Okay, so what is your net loss is the question. If your temperature was the same as the wall's temperature, then there would be no net loss or gain. Okay? But you're warmer than the wall, so you're losing net energy via electromagnetic radiation, and that's the net loss. Okay? So your temperature is higher than the temperature of the wall, of the surrounding. Okay. This number, emissivity, it's between 0 and 1. Okay, well, it's okay, so we will if it were 1, it was a perfect absorber and perfect radiator. It will be 1 if you shine any radiation on it and it will absorb all of it. Okay? And it would be 0 if you shine radiation of it on it and it doesn't absorb anything. It's a perfect reflector. Okay? So there's no such thing. So emissivity is between 0 and 1. Okay? An ideal absorber, also known as a black body, because it wouldn't reflect any radiation, it would absorb everything, is an object that absorbs all energy and its emissivity is 1. An ideal reflector absorbs none of the energy incident on it and emissivity is 0. So a good absorber is also a good radiator, and a good reflector is a poor emitter as well. So in the winter, you want to wear dark clothing because you want to absorb the radiation falling on you. Okay, and in the summer, you want to wear light clothing, so you reflect all the radiation falling on you. Okay, there's a couple of interesting topics. I know everybody's getting tired, so I'm just going to give you. Okay, I'll briefly tell you about the greenhouse effect. As young people, you ought to know about it. You guys all have heard about it, but I'll give you some numbers. Okay. And then we'll end the class. Okay, the average temperature of the Earth, 200 years ago, was 14 degrees Celsius. What do we mean by average temperature of the Earth? How would you measure the average temperature? So here's the rough idea. you break the temperature into grids, the Earth into grids, measure the temperature here all year round, get the time average. So let's say, do you guys know what is the average temperature in Florida?
82?
Okay, here's how you tell. You want the average temperature. You dig a hole, let's say 6 feet deep, and measure the temperature there. You don't have to do that here. You just measure the temperature of spring water, 72 degrees Celsius. That's the average temperature in Florida. Okay? Average temperature here, average and then take the average of these. That's how you get the average temperature of the Earth. Okay? So the average temperature of the Earth is 14 degrees Celsius. Now here's energy coming to you from the sun. This is coming in invisible light. That's the way. So this is the wavelength, it's shorter wavelength. This is the wavelength coming. Now, how much energy is getting to you? It's 1400 watts per meter square. So what that means is, so here's the Earth, and here's sunlight coming. Every meter square is getting 1400 watts per meter square. All right, part of that is reflected and all that. Half of that is absorbed by the Earth. Okay, again, this is, so you take this cross-section area, 700 watts per meter square times that. Okay, that's how much energy is absorbed. Now you'd better be radiating exactly the same amount. Otherwise, what will happen?
Average temperature is going to
Rise. Okay. So whatever you're getting, you'd better radiate out. So 200 years ago, the balance was exact. Okay. Now we've been radiating less for the last 50 years. And the Earth has been warming up. The current temperature is about 15.3 degrees Celsius. We want to be below 16 degrees Celsius. Okay. Why are we radiating less? Mm-hmm.
Keep on having gases that trap more heat.
So we are changing the property of the atmosphere. Okay. So we are changing the nature of the atmosphere. By adding CO2 is the main culprit. By increasing the amount of CO2. Okay, back here, 200 years ago, CO2 was 280 parts per million. So every million atmospheric atoms, there were 280 CO2 molecules. Today, that's 400 parts per million. What does CO2 do? So we are emitting infrared radiation. CO2 happens to absorb that radiation. Okay, and it'll emit equally in all directions. So essentially, infrared radiation gets trapped. Okay. So more CO2 there is, more radiation is trapped, and less radiation escapes. All right. Well, you can read all of that. Okay. How much less is being radiated now? About, so you can look this up, 3.2, something like that, watts per meter square. So for every meter square, we are radiating 3.2 watts less than what's coming in. That's called radiative forcing. You can look out So radiative forcing would be 0 if you were emitting an equal amount of what's coming in. Okay. Well, what does this amount to? Energy is being trapped on Earth at a rate of 1,600 trillion watts. This is about 100 times greater than the rate at which energy is being used all of humanity. But, well, that doesn't illustrate that. Okay, so remember, you're radiating 3.25 watts less per meter square. This is equivalent to exploding 20 atom bombs every second. For how long? Constantly. And trapping the heat. So what is our goal? To be below 16 degrees Celsius. Well, what's magical about 16 degrees Celsius? So the claim is if the temperature goes above 16 degrees Celsius, you wouldn't be able to stop the melting of Greenland ice shelf. All of that would melt and the temperature and the sea levels would rise by about 7 to 10 meters. That would displace about a billion people, 700 million people. Bad news. Okay. But I'm not worried about it because I'll be long dead. The problem is yours.